So magnetism. So this is another interaction that you can have between particles. And of course, we learned that we generally don't want to talk about direct interaction. We want to always do it in terms of field, right? So one thing makes field, other one feels field. Okay. So same idea. And I'm going to start on the effects side. Okay. So I'm going to say first I'm going to have this thing coming out of nowhere called a magnetic field, and I'm going to be interested in describing its effects on charged particles. Then later on we'll get to what causes a magnetic field. But let's start with magnetic field effects first. So start with magnetic field effects. And we'll work backwards from there. So here's what I'm going to do. I'm going to have, for comparison, what we're of course just leaving behind, a uniform external external electric field. Of course, that's the simplest electric field you can have. Is a uniform one. And I'm going to compare it to a uniform magnetic field. And what we use for that, we use B. So this is going to almost be kind of like a virtual experiment. I'm going to drop charges into this, both of these fields in turn, and I'm going to compare and contrast and see how these things are affected. So, start with the most basic thing. I'm going to drop a plus charge in there. And which way does it feel a force? To the right. Positive charges feel a force downstream. That's the electric force. So if I let it go from rest there, it will go faster and faster to the right. It will accelerate to the right. All right? Let's do the same thing in my virtual magnetic field here. If I had this in a lab, what would happen? Well, you drop a charge in there, and it would just stay there. So what does that mean about the magnetic force? What's that? So if you have an object at rest, staying at rest, that means it has how much force? Zero. The magnetic force is 0. All right, big difference right away. So clearly we have a different animal here. All right. The magnetic field has a very different effect on a particle than an electric field. All right, let's try some other ones, okay? Apparently, the magnetic field doesn't like particles at rest. It doesn't do anything to them. It doesn't have any effect on them. So apparently we have to have a charged particle moving, okay? So let's compare and contrast over here. Let's throw a charge with the field line like this. Which way is that going to feel a force? To the right. To the right, still to the right. Positive charges feel a force to the right. So it's going to accelerate to the right, go faster and faster. The only difference between that and the previous one is that instead of starting from rest, it got a head start, right? It already had a pre-existing velocity for which the electric force is going to build on, right? Make it go faster. Let's try it over here. We give it a velocity. It does go that way, but it doesn't get any faster. It just maintains the velocity it had that you gave it. What's the force? 0, right? Newton's first law. Sure, it'll just keep whatever velocity it already had because there's nothing forcing it to do it differently. So I guess I should label over here, these guys speed up. This is just constant speed in a straight line, constant velocity. All right, what do we have to do here to get the magnetic field to register its presence at all? Let's try throwing a charged particle against the field line. So if I threw a plus charge upstream to an electric field, what's the direction of the force? To the right. Still to the right. It's always to the, downstream to the field. What's that going to do? It's going to decrease the speed and then stop, and then if I keep letting it turn around and speed up another way, right? So, right? What if I did that over here? Well, it just goes off in that direction at constant speed, which means, again, no force. What do we have to do to get the magnetic field to register its presence? It's a lot more elusive here, so let's try different things. All right, well, let's put a charged particle and throw it like this. What will be the direction of the electric force on that? Still to the right. Positive charges feel a force to the right. And so what will happen is it'll get deflected like that. It'll fly in a kind of curved shape, much like projectile motion. Okay, it'll kind of form what's called a parabola, or just to be less fancy, an arc shape. Because what's going to happen is that the velocity it has in this direction is going to be maintained, while the electric force is going to make it pick up velocity in that direction. Okay. All right, let's try it over here. So we're going to throw a charged particle cutting across the magnetic field line. Not at rest, not going along with it, along the same line, but cutting across it. And now, we finally notice something happening. It does curve. Here's how it curves. It curves into the page. It curves like this. So it's not even in the plane of the page anymore. This is going to be one of the few topics in Physics 1 and 2 that is fully 3D. Okay? So, we need a way to notate directions that we can't draw on the page, to which I will suggest the following tool. Imagine you had like a Nerf arrow like this. Okay? It kind of has like a cone for a head and then crosshairs in the back, right? You can fire it out of your little Nerf cannon or something. If it is coming toward you, about to hit you, you will see this. Okay, the crosshairs you can't see, you just see through the cone that's about to poke you in the eye. Okay, this is out of the page. And if you fire in retaliation at somebody else as it recedes from you, you'll see it like that. Right? So you'll see the crosshairs, and then behind it, the back of the cone head. Okay? So this is into the page. Okay? So in my case, the direction of the force, as I told you, is into the page. I will notate it like this. Now, how did I get that? I'm going to show you there's a tool for working in these 3 dimensions. It's a mnemonic called the right-hand rule. I'll show you how that works. I'm not going to have time for it today. But at least, finally, we've gotten the magnetic field to register that has any kind of effect on a charged particle. And apparently, the thing that is necessary is for the velocity to cut across the field lines. If you don't cut across the field lines, then you won't feel a force. Now, of course, this is cutting across the field lines maximally, but you don't have to cut across them perfectly. You can also cut across them partially. So, for instance, you can have something that's like this. And what we might do is we might break that velocity up into 2 components, one of which is parallel to the field, and one of which is perpendicular to the field. And the reason why we would do that is because the parallel part clearly is irrelevant. We learned that if there was only a parallel part, like there was up here, magnetic field could care less about that. So there's no force due to this. Any force that you get is the fact that you have a component cutting across the field lines. Now, not the entire velocity, but some of it is. And I can point out here, while I didn't tell you how to get the direction of this force, if this is correct, then this is exactly the same direction, so I can safely conclude that the magnetic force must be in the same direction. Okay? So that is what it takes for a magnetic force to be exerted by a magnetic field, is that you have to cut across the field lines in whole or in part. Okay? So the magnetic field cannot exert a force except, so force only if you cut across the field lines. In other words, if your V perpendicular is not 0. So, with that in mind, let me compare and contrast the two laws. The electric force is easy. Of course, it has no motion dependence at all. You just take the charge and multiply it by the electric field. And of course, the direction is, for plus charges, feel a force downstream to the field, and minus charges feel a force upstream. That's the electric force. That's easy. And so since I was working with only plus charges here, of course, every single time we had the force just go downstream to the field, and that was it. Now, if I go over to the magnetic force, well, the size isn't really so much different. The size just has that one extra ingredient. It's right there in the middle. You have to have V perpendicular. If you don't, the whole thing goes to 0. And the direction is a little more complicated. As I mentioned, that's something called the right-hand rule. So I'll pick up here next time and show you how that all works. So that's it for today.